This is Introductory Nuclear Physics for undergraduate and graduate students. Today's topic is radioactivity, the carbon dating. I am Dr. Nasir M. Mirza, and today I will be talking about the carbon dating in detail. We will first review the radioactivity and the decay, the half-life, and the mathematics of half-life, then mixed isotopes half-life calculations, and then partly we will talk about the parent and daughter decays and secular and transient equilibrium cases. Then we will start the radioactive dating, the carbon dating, and we will try to figure out the ages of rocks and meteorites and the solar system, including Earth. The radioactive decay is the kind of uncertainty that has been created by the imbalance of the protons and the neutrons. What happens inside the nucleus is that there is instability generated due to the imbalance of the forces within the nucleus. And we would like to know the energetics whenever there is a nuclear reaction. What happens? We must know how it decays. A decay of A into B or B into C or A into B and C is possible if there is positive Q value of energy available for the reaction. And again, the masses are critical for this kind of substitution. And there might be a barrier, the Coulomb barrier, that can prolong the lifetime for such decays. So what we have learned previously is that the decay is described by the quantum mechanical framework, Schrödinger's framework, and relativistic quantum mechanics by Dirac. And it is purely a random process with a constant probability for the decay of a single nucleus that happens to give its state in a certain interval of time. Then we know that there are several modes, and except the case other than the neutron or the neutrino emitted from the nucleus, there is always a Coulomb barrier. The Coulomb barrier has certain height, and the particle which is within the potential and in the bounded state remains within the bounded state. And to get out of that bounded state, it has to gain energy and reach at certain higher level to penetrate through the Coulomb barrier. And the quantum mechanical treatment is showing us that there is a finite probability that the particle can get transmitted through this Coulomb barrier, and it can tunnel through, and the particle can also get reflected. The Coulomb barrier potential is given by Z1, Z2, E squared divided by R, that is dependent upon the charges, the charge which wants to leave the system, and the charge of the nucleus. If the barrier is there and it is possible that it will cause delays of the decay beyond the lifetime of the universe, then we consider the nucleus to be very stable one. Probably it will not decay. We have already understood the process of radioactive decay of alpha type and the beta type and the gamma type, and we have come to the conclusion that there is a half-life, which is the time that is taken for the half of the parent nuclei in the sample to decay into the daughters. And the radioactive elements really can be used to count the number of parents in the daughters in the sample, and we can reach at this result of the half-life. We can see a curve by plotting the number of counts as a function of time in which the parent elements are following an exponential law and going down, and the number of daughter elements, they start from the certain zero value and then start going up and get saturated. The increase in the daughter element or the decrease in the parent element can tell us about the half-life of the sample. The young objects have many parent nuclei and the fewer daughter elements, and the old objects will have few parent nuclei and many daughter elements. So there will be, you see, at the end of many half-lives, you will see the red color counts in a very large quantity and the blue color in a decreased manner. But originally, the parents are in large number and the daughter elements are in smaller number. This technique can be used to find out the objects on Earth and in the universe with the ages from few thousand to few billion years that we can measure and determine the lives. The radioactivity and its half-life has a very meaningful thing. It has its association with the lambda, the decay constant, the probability of decay per second. The larger the value of the decay constant, the rapid decrease in the radioactive sample will take place. The radioactive nuclei will go down rapidly if the lambda is large. The large value means the short half-life. Within short half-life, they will go to smaller values. The medium lambda values will have the intermediate half-lives, and the smaller lambda values, the probability of decay, will have a very large half-life, and therefore these elements will remain with a slow decaying probability, and therefore they will be there. So at any time, if you measure, you will find that the large lambda value elements will have smaller number, the medium will have intermediate values, and the smaller the lambda value, the larger will be the content available in the elements. We have already seen that if a sample starts with n not radioactive nuclei, then half of the sample will be left after one half-life. And this can be seen in this curve, that the 50% after one half-life, it becomes 50%. And the next 50% decrease will occur in the second half-life, and the next will be in the third half-life. So after two half-lives, the half of the half will remain, and it will be a half square. And after three half-lives, it will be half of the half of the half, which means 1/2 to the power 3, or 1/8 of the nuclei will remain. So after five half-life, we can safely say that the original parent nuclei will be very small. In general, after y half-lives, there are 1/2 to the power y multiplied by n elements left, and the y is the number of half-lives. This formula even works for the fractional half-lives as well. For example, 0.1/2 of the half-life will be 0.933 times n nuclei left. So mixed isotopes, if we are using in a sample, then we will find that the total radioactivity will behave like this, blue colored line. If we have an element which is decaying with a half-life of 1 day, and then there is another element which is decaying with the half-life of 5 days, then the superimposed overall sample will be showing this kind of total activity. Originally, it will be obeying the one day half-life rapidly decreasing effect, and then eventually it will be showing the 5 days half-life effect. The total activity is basically the sum of the individual activities. The first contribution comes from the T1, And the second contribution comes from the T2, the second sample. The total activity curve has eventual slope for the longest half-life, and the curve is basically the subtracted from the total curve to give the short-lived curve, which is called the curve stripping. So we can figure out this radioactivity by subtraction, and we can find out how much is this. And we can always find out the total activity at the end, because it will be predominantly due to the longer lived isotope. For a single radioactive decay into a stable element from A to B, the radioactivity will be obeying this e to the power minus lambda t relationship. That is the exponential radioactive decay. But for an element which is going to decay into an unstable B element, which is going to decay into a stable C, then the differential equations will be the Boltzmann's equations. The first equation is about the parent, in which the similarity you can see that the rate of change of the parent elements with respect to time is directly proportional to the number of elements of the parent nuclei. And the lambda parent is the decay constant for the parent, and it is related to the half-life of the parent. The second equation is telling the rate of change of the daughter elements number with the time, and it has a term in which the decrease in the daughter elements is taking place, and it is proportional to the total daughter elements with the minus lambda d, which is the decay constant for the daughter element. The minus sign is telling us that it is a decrease. The daughter element is also decreasing as a function of time. However, the parent elements that are changing into the daughter elements are contributing to the daughter elements. Therefore, this lambda p times np is the source term for this equation. If you solve this equation for the daughter element, you will reach at this result, in which within the parenthesis there are two competing factors, e to the power minus lambda p and e to the power minus lambda p, one for the parent and one for the daughter element. And the eventuality is the decay of the daughter elements. So at time t is equal to 0, the daughter elements are equal to 0. So in terms of radioactivity, the complete solution can be written like this. The parents are going to exponentially decrease as a function of time. The daughter elements are going to increase first and go high and then come down. Let us talk about the secular equilibrium. It is for those where the half-life of the parent isotope is long. Half-life is long, therefore Tp, the half-life is too large, which implies that the decay constant is nearly 0 for the parent. And therefore the decay constant for the daughter is there. And therefore this is a sort of 1 minus e to the power, which is indicating a saturation, that the daughter elements will grow and will become saturated. And the parent elements are nearly constant. They are decreasing, but not so much for the measured times. So within the 10 half-lives of the daughter elements, we see a very small change. You see, for a comparison, we have drawn a sketch for half-life of the parent equal to 10,000 years, and the daughter element has only 50 years. So it is rapidly decreasing as compared to the parent. So parents are really very, very slowly decreasing, but the daughter elements are increasing and saturating. So in this case, the parent and daughter are said to be in secular equilibrium. Transient equilibrium is another example in which the half-life are longer, but they are not infinite. The parent's half-life is long, but it is not infinite. For example, 1,000 years of the parent half-life and 500 years for the daughter. And this kind of a case generates the transient equilibrium, in which the parent isotope's half-life is long, but the value is not infinite. Then the parent-daughter activities are in constant ratio. So for longer periods, if you see that their ratio will be a constant ratio. And that is what we call the transient equilibrium. The activity is really governed by the half-lives, and the ratio is dictated by a constant. The T parent divided by T daughter minus the T parent is the dictation given in the activity ratio. No equilibrium case is when the daughter's half-life is long than the parent's half-life. There is no equilibrium then. The parent activity is going down like this, and the daughter activity is increasing and then decreasing. But we cannot figure out any relationship between the ratios or the values. They are really independent of each other. Here is the example of TE at the meta state of 131 and the half-life of 30 hours. Its daughter is iodine 131, and it is with the half-life of 8 days. Comparable almost, and the figure shows that the buildup and decay of the daughter product takes place. It increases and reaches a maximum and then starts decreasing again. But we cannot figure out any equilibrium condition or a relationship between the daughter and parent. So no equilibrium can be figured out when the parent and the daughter half-lives are in such a way that one is comparable or one is more as compared to the other. Let's talk about the half-life further. Here we show in one part of the table the time in the half-lives. For example, we see here 10 to the power 6 nuclei, the one half-life decreases it to half of its original number. Then second half-life decreases it further to 250,000. And then third half-life decreases it to 125,000 and so on. And after, we can see that after about 10 half-lives, it is about 2,000 value as compared to 1,000,000. So it becomes insignificant after 10 half-lives. For example, instead of writing down the half-lives, if we are really given with the half-life value, for example, 5,730 years is the number, then 100% will go to the 50%, and then to 25%, and so on, and the value will become fraction in percentage after the 9 half-lives. One can safely say that after 5 half-lives, the value is less than a fraction. Therefore, we say that now they have gone to very, very small value. The radioactive dating started with the knowledge that there are elements that are in nature having larger values of the half-life, and their ratios can be figured out with the other constants, and then we can use them for the dating. The original proposal came from Rutherford and the group, and the things progressed. The elements that are being used for the radioactive dating include carbon-14. The daughter element is nitrogen-14. The half-life is 5,730 years. The potassium isotope, potassium-40, its daughter argon, and it is 1.25 billion years. 10 to the power 9 is billion. Uranium-238 leading to lead with the 4.5 billion years. The thorium leading to lead-208, 14 billion. Rubidium, samarium, uranium, and we can have the half-lives of as large as 704 billion years. This is what we call the radiometric dating or age measuring thing, in which the parent and the daughter ratios are used. Let's first figure out which one is used where. Uranium-238 and the daughter element lead, they are employed using minerals like zircon, uranite, and the other metamorphic rocks to figure out the dating ranges of 10 billion to 4.6 billion years because of the half-life. Similarly, potassium-40 and the argon-40 can be employed to figure out the volcanic rock dates from 0.05 billion to 4.6 billion years. The rubidium and strontium can also be employed to figure out the ages of rocks. The carbon-14 and the nitrogen-14 can be employed to find out the 100-year to 70,000 years age of wood, charcoal, and the other structures like bones, tissues, minerals that have the water and the dissolved carbon content in it. Let's talk very briefly about the carbon dating. Cosmic rays, the solar electrons, the protons, and the neutrons, they enter into Earth's atmosphere and hit the atoms in the atmosphere, and they give off the energy and the energetic neutrons. The neutrons collide with the nitrogen-14 and create the carbon-14. Our atmosphere is filled with nitrogen-14. They create the carbon-14, and then the isotope of hydrogen, one proton and one neutron, the deuteron. The living bodies then continuously absorb the carbon-14 as CO2 in the photosynthesis. And when we see that the plant and animal dies, it is no longer consuming the carbon-14. Then carbon-14 starts decaying with the half-life of 500 and 5,730 years, and they will emit the electron in the process. This electron emission rate will tell us the counts and the age of that thing which has consumed and was in equilibrium, and from the time it stopped consuming to the time we are measuring, we will come to know the age. Let's do one example on this. An archaeological dig, you uncover an old wooden bowl. With your radiation detector, you measure 560 counts per minute coming from that bowl. Each of these counts correspond to the beta minus decay of carbon-14 atom into nitrogen. This nitrogen is nitrogen-14. Using the same kind of the wood, but from a tree that was recently cut down, you make a similar bowl of the same shape and the size and the mass that you have from your site. Then this recent bowl is measured and it registers about 800 counts per minute in your detector. Question is, estimate the age of the old bowl you have unearthed. So we continue with the solution. Our working assumption is that the old bowl would have emitted 800 counts per minute originally when it was first made from the wood and from the trees that was recently cut. So this assumption makes that the ratio of the carbon 14 to the carbon 12 in our atmosphere has remained constant over the time, which is approximately true. So we can get a good estimate of the age of the bone without any corrections. And we can apply the decay equation that at this time it is 560. If it was at the time t is equal to 0, when it stopped consuming the carbon 14, it was 800. Then using the exponential law e to the power minus lambda t, we can find out the time. The lambda is coming from the half-life. So taking the natural log on the both sides of this equation, natural log of 0.7 is equal to minus lambda times the time. And we get the t is equal to natural log of 0.7 with lambda with minus sign. And by substituting the value of lambda in terms of the half-life, it is t half divided by natural log of 2. And simplifying the whole thing in terms of the t half-life, which is 5,730 years, we reach at the result that the answer is 2,900 years. So our conclusion is that the site you are exploring contains artifacts are from the time of about 3,000 years ago. Similar examples are used to figure out. This is Pharaoh's boat that was found in Egypt, and it is about 4,500 years of age from the analysis of the wood samples and the carbon dating of the similar type. Now we talk about the uranium dating, the decay of uranium-238. Uranium decays into 8 alpha decay steps as shown in this figure. You start with the uranium, which is 4.5 G years, which means million years. I'm sorry, the billion years. It is about 10 to the power 9 years. And then it decays into the other elements and comes to thorium, and then it goes to the rubidium, and then it keeps on decaying to the polonium and the barium and the lead, and eventually it becomes stable at 206. So uranium decays into 8 alpha decay steps with the 6 beta decay steps with the series, and the half-life of the uranium-238 comes to be about 4.5 into 10 to the power 9 years. So all the minerals that are the zircon minerals, the ZnSiO4, zinc silicate type, contain uranium traces and uranium in traces amounts and can be used to date the rocks in the similar fashion that we have gone through. To figure out that, we must know that it is what is the value now and what was the possibly its ratio. The oldest rock on Earth is mineral zircon. It contains uranium traces. So zircon from Australian rock indicates that the age of 4.4 thousand million years is for that rock, which is 4.4 billion. The quartz from the same rock reveals that the water existed on Earth at that time. So Earth is probably older than that, and we believe that it was initially molten. That is why the rock formed after the Earth cooled down, and therefore, roughly speaking, it is more than 4.4 thousand millions of years of age. Let's see another example. Uranium, the parent element, is eventually converted into lead, the daughter element, and a granite contains the crystals with 150 parts per million ppm, by atomic proportion of uranium-235 and 1050 ppm of lead, Pb-207. The half-life decay of uranium-235 to lead is 700 million years. Question is, how old is rock? So what we know is the parent and the daughter parts per million crystal values, 150 parts per million in atomic proportion of uranium and 1050 ppm of lead, so it's about 1200. This is the original number of parents that are present at the time of the chemical reaction that formed the mineral in the rock. We know that the half-life of uranium is 700 million years, so uranium parent will decay by half to 700 million years. So today's level is 150 ppm. So 1200 divided by 2 gives us 600. 600 divided by 2 gives us 300. 300 divided by 2 gives us 150 ppm. So this is the today's level. After one half-life, the second half-life, the third half-life, it is at the level of 150, the 150 parts per million in the atomic proportion of uranium. So we can say that the 3 half-lives have passed since the rock was formed. Therefore, 3 half-lives multiplied by 700 million years is equal to 2,100 million years, or 2.1 billion years. So this rock sample is 2.1 billion years old. Similar dating methods have been found using the potassium-40 isotope of potassium, which is unstable, and it is used for moon rocks. It decays to stable isotopes of argon, argon-40, and the technique which is used to date is called the potassium-argon dating. The decay rate is slow. The half of the potassium atoms decay in 1,250 million years. So about 3.6 half-lives of potassiums have happened since the formation of moon. So the most of the lunar maria erupted between 3.8 to 3.6 billion years ago, and they cooled and began to retain the argon and argon of that period. So we can use this ratio to find out. Using the isotopes of rubidium and strontium, the rubidium-87 and strontium-87 or 86, the age of the meteorites can be determined. One of the two naturally occurring isotope of rubidium-87, decays into strontium-87 with the half-life of 49.23 billion years. Very large half-life. Daughter element strontium-87 produced in this decay is only one of the 4 naturally occurring strontium isotopes that were not produced exclusively by the nuclear synthesis in the stars. So over the time, the decay of the rubidium increases the amount of strontium, while the amount of other strontium isotopes do not change. Therefore, the ratio of the strontium and the 87 and the strontium 86 in a sample can give you an accurate measure of the mass and let you know the time. You can measure this with the mass spectrometer, and when the amount of strontium and the rubidium isotope in the sample is determined, the age can be calculated with the help of this ratio, strontium 87 and strontium 86. So very large half-lives, like billions of years, for 49 billion or 50 billion years, the ages can be measured. Let's talk about the age of the solar system from all this. It comes through meteorites. Similarity in the ages of meteorites, the moon rocks, and the old rocks on Earth suggest that the solar systems were formed together. The idea is that the gravitational attraction brought together the gases that condensed into dust, and then dust became the flat disk, and that is about the sun. And eventually the dust collapsed into a large bodies, and some of the large bodies again got converted into the planets. So the oldest material on Earth, the moon, and in the meteorites dates back to the original condensation of the dust particles in the disk around the young sun. And this is the material which can be figured out with the help of the dating. This point of time is taken as the beginning of the solar system, and the current accurate accepted age of the solar system comes to be 4.5 into 10 to the power 9 years. So we can finally talk about the age of Earth from radiometric aging age dating. Radiometric age dating measurements are really with the help of uranium-rich rocks. We measure lead and show that some of these minerals were more than 1 billion years of age. The oldest such minerals were analyzed to find the age. The crystals of zircon from the Jack Hills of Western Australia, they show that they are more than 4.4 billion years of age. Comparing the mass and the luminosity of our sun to the multitudes of the other stars, it appears that the solar system has the age of same value near that of these rocks. So oldest known solid constituents within the meteorites formed within the solar systems are about 4.567 billion years of age, and that seems to be the age of Earth. This is the age of the solar system, and it forms the upper limit for the age of the Earth. Being part of the solar system and developed through the collapse of the material around the sun, it is the conclusion that we draw that about 4.567 billion years, and billion means 10 to the power 9. We stop our lecture here, and our next lecture will be focused on the fission reactions and how they occur. Thank you so much.